Today's lesson will be on Coulomb's law. We all know that like charges attract and unlike charges repel. But how much force is involved? And does it matter what the charges are or how close they are? The answer is yes, and this is summarized with what's called Coulomb's law. The magnitude of the electrostatic force exerted by one point charge on another point charge is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between them. This is summarized by this equation, where this is the force, the magnitude of the force. That's why these are in absolute values. K is a constant, so this is the charge on one object, this is the charge on the other object, and this is the distance between them squared. Okay, here's our equation. Here's our old friend, Newton's law of gravity, and you can see they're very similar. They're both inverse squared relationships. They both depend on some property, like this one's charge, while this one's mass. And the difference is that this can either be attractive or repulsive. Well, this is always going to be an attractive force. Okay, let's look a little closer at this equation. Sometimes this constant here is expressed in what's called permeability of free space. We're not going to really deal with it in our class, but I just wanted to introduce it to you in case you see it again, where K can be expressed as 8.99 times 10 to the 9th newtons meters squared per coulomb squared, but it can actually be 1 over 4 pi epsilon naught, where epsilon naught is this term here. In this class, you're really not going to have to worry about it too much, but I just wanted you to be introduced to it, or we're going to be using this term here for K. Alright, so let's try an example. In the Bohr model of the hydrogen atom, the electron is in orbit around the nuclear proton at a radius of 5.29 times 10 to the negative 11th meters. Determine the speed of the electron, and we're going to assume it's a circular orbit. So this is a cool problem because it's combining the idea of electricity that we're learning now in Coulomb's law and centripetal motion and centripetal forces and accelerations as we did in prior chapters. Alright, so we know that the sum of the forces are causing this centripetal acceleration, and we know this from Newton's second law, that it's the sum of the forces cause the acceleration. And the only force in this case acting on it is the electrostatic force, so that we know that we can use Coulomb's law to find this, and we can set it equal to this. So we're going to solve first for this electrostatic force. And here we just put the numbers in. We have our K value. We have two charges. Now, why do I have it squared? Because K and Q and Q are the same value. One's a proton, one's an electron. And this is the distance between them squared. And this is what the force comes out to be. Now, is this an attractive or repulsive force? Well, you should understand that it should be an attractive force because one of the Q's was positive, one of them was negative. And since I only used the absolute value, this F came out to be a positive number. So once we know this force, we can set it equal to mv squared over r, and we can solve for v. So the F in this equation is the F we just solved for. R is the radius divided by the mass of the electron, and we can see what this speed is that it needs to maintain a circular orbit. Alright, so let's try another problem. Here we have, we want to determine the force on Q1 by Q2 and Q3. Now, the force on Q1 in the middle due to Q2 is an attractive force because one's positive, one's negative, and it will be pulling it to the left. The force on Q1 due to Q3 is a positive attractive force as well because one's positive, one's negative, but this time it's pulling it to the right. So if we want to find out the net force, all we have to do is add those two together. It's just the sum of those two forces. So this is a very simple example. We found the force of attraction between Q1 and Q2. Use the two charges, plug them into the equation, and the distance between them squared, found out the force. and that's an attractive force. And between Q1 and Q3, here's the charge, here's the charge, divided by the distance between them squared, and that's also an attractive force. So this is where it may get a little tricky. I'm going to assume to the left is negative, so that means to the right is positive. So that means we have a negative pulling to the left and a positive pulling to the right, so the net force is a force of 5.7 newtons to the right. So this whole thing would end up being moved to the right because there's a net force acting on it and it will accelerate.